Lesson 7-4, proving triangles similar. Just like the theorems that we use to prove triangles congruent, we can also use similar theorems to prove them to be similar. The key here is to recognize which one you're using and make sure you use the little similarity symbol after the postulate. The first one is the AA similarity postulate. This tells us if we know two pairs of angles are congruent, then we know that the triangles would be similar. This should make sense. For example, in this case, I can see that 115 degrees is congruent in both of those. 36 degrees is congruent in both of these triangles. And I could go calculate the third angle by adding together the 36 and 115. And by this, we're going to get 151. And then we do 180 minus 151. And this is going to give us 29. So I know that this is a 29-degree angle. Since I have the same numbers, I would do the same thing to get this to also be 29 degrees. We really only need two angles for our AA similarity postulate because of this reason. So to prove the angles similar, all I have to know is that two pairs of angles are congruent. So our postulate would read, if angle A is congruent to angle D, and angle B is congruent to angle E, then I know that triangle ABC is similar to triangle DEF. Let's look at the next postulate. The SAS similarity theorem tells us that if an angle of one triangle is congruent to an angle of the second triangle, and the sides that include the two angles are proportional, then the triangles are similar. Notice that we need congruency on the angles and proportionality on the sides. So in this case, what we're looking at is if AB, that would be this side right here, is over DE, because those two sides correspond, is proportional to AC over DF, and I believe your book says DR, that should be DF. And we know that angle A, the angle between those two sides, is congruent to angle D, then we know that the triangles are similar by our SAS similarity theorem. So let's take a look at an example of this. In this one right here, we can see that angle D and angle A are congruent. So all we need to do is check the proportionality of the sides. So what we're going to do is look at a ratio from one triangle to the other. So DE is 24 and AB is 18. I can reduce this fraction and come up with a ratio of 4 to 3. Now let's test the other sides, because we've tested this side. We still have to test this side and make sure it's the same ratio. 36 to 27, when I go reduce this, I also get 4 over 3. Since my ratios are the same, I know that my sides are proportional. Therefore, I can say that triangle DEF is similar to triangle ABC, and my reason would be SAS similarity. Our final theorem for similarity is the SSS similarity theorem. Just like you would expect, this means that all three pairs of sides have to be proportional for the triangles to be similar. And if you remember, we're going to check this the same way we did in the last one. So we're looking at AB to DE, and we're looking at BC to EF, and we're going to compare that to AC to DF. And you do have to check all three ratios to make sure that they are the same, because it's possible for two of them to match and the third to be different. So our formal definition says that if the ratio of AB to DE is equal to the ratio of BC to EF and the ratio of AC to DF, then the two triangles have to be similar. So let's look at what this looks like in terms of being a proof. You're very used to proving triangles congruent. Proving triangles similar is very similar, no pun intended, and you just have to make sure that you know what you're looking for. So I want you to take a look at this one and address this one on your own. I think you have enough proof skills to be able to do this. Stop the video, try to write out this proof, and then resume the video and check your proof. Okay, we should have our setup, and you should have had no trouble filling in your given. Anytime I see parallel lines in a given, I start looking for alternate interior angles. So if EF is parallel to HI, that makes EH a transversal, so my alternate interior angles would be these two angles right here. So by the alternate interior angles theorem, we have angle FEG congruent to angle IHG. Now, if I'm going to use AA similarity, I need another pair of congruent angles. Hopefully you're seeing your vertical angles right here. So let's write up what that would look like. So now to finish off the proof, since I have two pairs of congruent angles, I can go ahead and state that triangle EFG is similar, not congruent, to triangle HIG, and my reason would be AA similarity. Now let's look at the next proof. We've got a pair of lines that are told to be perpendicular, and we've got some proportional sides. Our job is to prove POL, the small triangle, to be isosceles. So think through what that means. You would either need to know pieces of the side to be congruent, which would be very difficult to get, or congruent angles. So look at those angles and think if there's a way that you could get those. Stop the video, give this proof a try, and then resume the video. Okay, so here's our given. So let's use the fact that those lines are perpendicular to figure out what that means. If these are perpendicular, I know that those are right angles. So we can use the definition of perpendicular to make that statement. Once I've made that statement, I can say that they are congruent because we know that all right angles are congruent. So now that we've got these two angles congruent, I need to look at the sides around them so I can get those proportional. And if you look at what they gave us KJ to NM is proportional to JL to MO. So I've got those sides around the angles, which means I can say that the two big triangles are similar. Now, using the definition of similar figures, I can get those small angles that I need congruent to each other, therefore proving my triangle isosceles. Here's what the rest of the proof would look like. I have angle KLJ congruent to angle NOM because I've proven that those are similar figures. The converse of our isosceles triangle theorem says that if we have two congruent angles, then we have an isosceles triangle. So our final step would be to say that triangle POL is isosceles, which is what we were asked to prove, and our reason for that would be the converse of our isosceles triangle theorem. And we've reached the end of our proof and the end of our notes. Make sure that you go on and do your Tier 1 assignment and your knowledge check.